Dear session chairman and audience, welcome to our presentation. This study is about excess heat in a deuterium hydrogen to nickel palladium reaction system with multiple oxidation of the nickel palladium alloy powder. The work was done by Hong Zhang and Chen, Qiuran Lab, Xi'an, China. There are 4 parts for this talk. First, background. Second, methods and experiments. Third, results. And last, conclusions and discussions. For the background, we would like to bring you back first to our previous work, which was reported in ICCF24 last year. In this previous work, we built a D2 hydrogen and nickel palladium reaction system with customly made calorimetry system. As shown in the upper left, for the reaction fuel, we used palladium-coated nickel mesh, and the reaction vessel was filled with hydrogen or deuterium, while we have a heating inside the reaction vessel. For the calorimetry, we had Seebeck elements to measure the temperature of the inner cavity of a water jacket, also 2 PT100 sensor to measure the temperature of the water. And the temperature was transformed to output heat power based on the calibration of our blank experiments. To support this reaction system, we set up power suppliers, molecular pumps, water baths, and online data recording computers in Qiuran Lab, as shown in the bottom right. The results of our previous study shown that we can observe about 2 watt excess heat, but at very low filling pressure of deuterium, as low as 10 Pascal. When the filling pressure of deuterium was higher than 60 kilopascal, there was no excess heat observed. So the objectives of this study was to get higher power of excess heat. Very simple. Okay. We hypothesized that there might be 3 ways. First, adjust filling pressure of deuterium or hydrogen, which we tried and didn't work very well. For the second, change the reaction fuel. And third, maybe we can try other fuel activation mechanisms beside heating. Inspired by the study of Dr. Storms and Dr. Takahashi, we decided to try oxidation of the reaction fuel first. So here's a system we reported this year. There were a little bit modification different from the system we reported last year. So first of all, we replaced the palladium-coated nickel mesh with a smaller reaction vessel containing nickel palladium alloy powder, as shown here. And the heater, input heater was drawn in the smaller reaction vessel inside a big vessel, which were all inside a water jacket. And the calorimetry part was pretty much the same as the previous study. we made a total of 200-gram alloy powder by ball crusher. So the mass ratio of nickel to palladium was 40:1. It took 60 hours for us to get powder crushed. After cooling and drying, the powder, as shown in this photo, was placed in the reaction vessel we mentioned in the last slide. Here's a figure of the entire experimental procedure. As you can see, we filled in hydrogen, deuterium, and air sequentially and repeated this procedure 4 times. The hydrogen and deuterium was input for reaction, while the air was input for oxidation of the alloy powder. Before filling each different gas, we applied vacuum pumping. So keep in mind that the pressure of filling gas was very high. For deuterium, it was 300 kilopascal. For hydrogen was 500 kilopascal, and air was 180 atm. So each reaction procedure took about 72 hours, while the oxidation took about 24 hours. So the total experiment took about 30 days. Here's a detailed look of the results, which was the reaction of the hydrogen with our powder after second oxidation. As you can see that while we adjusted the input heating power, after rebalancing, we can observe different level of stable excess heat power, from maybe 0.3 or 5 to over 1 watt. So we plot the mean value of output excess power at different conditions. As you can see here, it was about hydrogen, and with different oxidation status of the alloy powder at different input heating power. So as we can see that after second oxidation, while the input heating power was above 200 watts, the excess heat power was significantly increased up to close to 2 watts. So that in that case, the reaction temperature was about 340 degrees centigrade. The deuterium case was a little bit different. We see an increase of the excess heat power until the third oxidation, and the excess heat power reached above 2 watts at the input power of 250 watts, which means the reaction temperature was about 380 degrees centigrade. Okay, to summarize, by replacing the palladium-coated nickel mesh, which was in our previous work, with the nickel palladium alloy powder of this experiment, reproducible excess heat was observed with the filling of 500 kilopascal hydrogen or 300 kilopascal deuterium in our reaction system. The excess heat power was increased with multiple oxidation of nickel palladium alloy powder, and it has to be at the optimized input heating power. To be more specific, we observed 2 watts of excess heat at the 200 and 50 watts of input heating after third oxidation of the nickel palladium alloy powder for both hydrogen and deuterium. Frankly, this level of excess heat was far less than we expected. But we believe we were on the right track because the reproducibility and it was output at very high feeding pressure of deuterium and hydrogen. So for the future studies, we will further optimize the composition and the configuration of the reaction fuel, and we maybe try some other mechanisms of fuel activation rather than simple heating. We would like to acknowledge Professor Akito Takahashi, Dr. Edmund Storms, Professor Xingyong Li, Dr. Wushou Zhang, Dr. Bob Higgins, Mr. Jed Roswell, and the most importantly, ICCF24 Organization Committee. Thank you for your attention.